All right, today's do now. Solve each limit problem. Pause the video, give each one a try, and then continue the video to hear the answers. All right, let's take a look. So our first one here is the limit of 3x plus 2 over negative 6x minus 6. If we rewrite this, we get 3x over x, 2 over x, negative 6x over x, minus 6 over x, right? And the limit as x approaches infinity. We recognize that every single term that has an x in the denominator after canceling will result in a 0. So we have this 3, 2 over x, negative 6, 6 over x, the limit as we approach infinity. So we recognize this goes to 0 and this goes to 0, and we're left with this 3 over negative 6, or negative 1/2. Now, you may have noticed yesterday a couple of interesting things. You may have noticed that when the degree of the numerator and the denominator were the same, that the limit as we approach infinity was simply the ratio of those coefficients. Okay, I'll note that one more time. So when the degree of the numerator and the denominator are the same, when we approach infinity, it is just the ratio. Now, the second one here, we have negative 8x over x squared, 2 over x squared, negative 5x squared over x squared, and 4 over x squared. And that becomes negative 8 over x, 2 over x squared, negative 5, and then 4 over x squared. And then once again, anything that has an x in the denominator goes to 0, and we're left with 0 over negative 5, or 0. Now you may have noticed yesterday that anytime the degree in the denominator is larger than the degree in the numerator, that it was going to be a 0. All right, and then let's look at this one. The limit as x approaches infinity, 7x squared over x squared minus 4 over x squared, x over x squared plus 2 over x squared. I'm hoping very quickly you recognize this is not going to work because, well, we cannot divide by 0. So how about we instead this time try to divide by the smaller of the two. So 7x squared over x minus 4 over x, x over x, and then 2 over x. So once again, note here, I decided not to divide by the larger degree because I was going to get a 0 in the denominator. So here we have 7x minus 4 over x, 1 plus 2 over x, and then approaching infinity, that goes to 0, that goes to 0, and then we get here the limit as x approaches infinity of 7x, which goes to infinity. All right, let's take a look here. We have the limit of x cubed as x approaches negative infinity, and the limit of x cubed as x approaches infinity. Note here, the behavior of this function is that it goes up to infinity as we move towards infinity, and it goes down towards infinity as we move to negative infinity. So we're going to say then, just by looking at the behavior of the graph, that the limit of x cubed as we approach negative infinity, mathematically speaking, note, is negative infinity cubed, which is a negative times a negative times a negative, so it's negative infinity. And mathematically, we are allowed to multiply infinities. And then we have the limit of x cubed as x approaches infinity. Note that's infinity cubed, which is infinity times infinity times infinity, which is also infinity. Now, do understand the idea here. We're not actually multiplying these. It's more conceptual. It's just we have bigger infinities as we multiply them. All right, now let's take a look here. So mathematically, we are not allowed to say infinity squared minus infinity, okay? Because we are not, both of these are unbounded, but we don't know which one is larger oftentimes. And so what we're going to do, we're allowed to multiply infinities and add infinities. We're going to rewrite this as a product because of that fact. So we're going to pull the x, factor it out, and then we're going to recognize that this is mathematically the limit as x approaches infinity of x times the limit of x minus 1 as x approaches infinity. This function goes to infinity as we go to infinity, and then this other function also does. And infinity times infinity is infinity. And we look at the graph, that is exactly what's happening. All right, let's take a look here. So, like I just said a moment ago, we are allowed to add infinities, and we are allowed to multiply infinities. But we are not allowed to subtract infinities or to divide infinities. So we look here and we notice this problem is a division of infinities. So what we're going to do is try to change that. So we're going to try to rewrite this in a way that it is a product instead. So let's say then that this is the limit as x approaches infinity. And then in the numerator here, let's factor out an x. And then let's separate this. So let's make this the limit as x approaches infinity of x over 3 minus x times the limit as x approaches infinity of x plus 1. Now, this first one we know because we have the rule from yesterday. We can divide everything by x, becomes the limit as x approaches infinity of 1 over 3 over x minus 1. And then using the theorem from before, that's 0, and this becomes 1. Now for our other part, we know this here is going to just be infinity. So times infinity, times infinity. So this goes to infinity, because 1 times infinity is infinity. Now looking at the graph, we can see, we can see that that's not true. Okay, let's backtrack. Note here, this on the denominator is 0 minus 1, so it's 1 over negative 1, so it's negative 1. So negative 1 times infinity is the negative infinity. As we approach infinity, this goes down to negative infinity. All right. Sketch the graph of f of x equals x minus 2 squared times x plus 3 by finding its intercepts and its limits as x approach negative and positive infinity. All right, let's start with our x-intercepts. Okay, so mathematically speaking, we know that the x-intercept occurs when y is equal to 0. So we're going to simply set this function equal to 0. We have x minus 2 squared, x plus 3, and the question is, when is it equal to 0? Using the zero product property, we see then that x minus 2 equals 0, or x plus 3 equals 0 for that product to have a value of 0. So x is equal to 2, and x equals negative 3. So we have x-intercepts at 2, 0, and negative 3, 0. All right, now let's find our y-intercepts. Now we know that we have y-intercepts when x is equal to 0. So find f of 0, which is 0 minus 2 squared, 0 plus 3. That is negative 2 squared times 3. That is 4 times 3, and that is 12. So our y-intercept is at 0, 12. All right, now let's find those end behaviors. So we'll start with the limit as we approach negative infinity of our x minus 2 squared times x plus 3. In this case, that is essentially negative infinity squared times negative infinity, which is infinity times negative infinity, which is then negative infinity. And then the limit going the other direction towards positive infinity. Apologize for my handwriting. I'm trying to use just the tip of my finger on my screen. Times x plus 3. And this time it's infinity squared times infinity. So that's infinity times infinity, or infinity. Now this should give us enough information to get a nice sketch. We know we cross at 12 on the y-axis, at negative 3 on the x, and at 2. We know that because this x squared produces this root or x-intercept that's 2, that creates in math what's called a double root. And this double root means it will bounce at that point. So from the negative infinity side, we're going to negative infinity, so we're going to go down. We're coming up and hitting 12, and we're bouncing at 2, and then we're going up to positive infinity, which satisfies the end behaviors as we see here. And then, of course, make sure it actually hits. All right, now let's give it a try. So complete textbook pages, page 130, 75 through 79. Message me if you have any questions.